Alright, let's also solve this other integral here. And to clear it up, we're solving the integral e to the 2x cosh, right, the hyperbolic cosine of x dx. If you do not know what the hyperbolic cosine is, that's not a big deal. You can easily search that and find out what it is. The cosh, right, cosh, or hyperbolic cosine x is e to the x plus e to the minus x over 2. Right, that's what cosh is. And the sine hyperbolic is e to the x minus e to the minus x over 2. But this is not important for this question. Knowing the definitions of these two functions is not important for this question because the main property is already described here in the statement of the problem. When you derive the cosh function, you get the sinh function, right, the hyperbolic sine. And when you derive the hyperbolic sine, you get the hyperbolic cosine. So these will behave just say like sine and cosine, except there's no negative sign change when you derive cosine. You get negative sign. This doesn't happen with hyperbolic cosine, right? The derivative of hyperbolic cosine is positive sine, hyperbolic sine, and the derivative of hyperbolic sine is also positive hyperbolic cosine. In turn, this also means that the integral of hyperbolic cosine, right? You antiderive, you get sine, and you antiderive sine, you get hyperbolic cosine as well. So that makes this prone territory for integration by parts. So it's very easy to integrate these functions. You could also derive these forever. You'd never stop deriving. These would never become 0. And you could also derive this forever, and this will never become 0. So this is probably prone territory for integration by parts, like I said, but we're probably going to use a trick which involves integrating by parts twice, and then looking at the quality of the equation that turns out to show up and solving for the integral that we want. So we will do that. Let's go. Let's start with integrating by parts. So I will derive this. So this is going to be, remember, integration by parts. Integral u dv is uv minus the integral of v du. So that's integration by parts. And we're going to use this. So think about what we should choose as our u and as our dv. It really doesn't matter much, but I will choose u as e to the 2x and then dv as the rest, because cosh is very simple to integrate. The antiderivative of cosine hyperbolic, like I said, is just sine hyperbolic, so it's going to be pretty simple. So when u is e to the 2x, then du is 2e to the 2x. That's the chain rule. And then when dv is cosh x dx, then move it to the side a little bit. The antiderivative is just sinh, so hyperbolic sine. And then this turns into uv, right? So e to the 2x. So let me actually write it out. E to the 2x. That is uv, so e to the 2x minus the integral of v du, so 2e to the 2x x dx. The 2 can come out, so this is e to the 2x. And note that we are back at where we started, not exactly, but with a similar problem as the one we started. We wanted to solve this first, but now we have to solve this that's very similar. That's a slight problem because we can't solve this easily either. The other way we have to solve this is, again, to use another integration by parts. So I will repeat my thought process and say that this is u and this is dv. So when u equals e to the 2x, the derivative is 2e to the 2x, and then the antiderivative when dv is sine hyperbolic dx, then v is the antiderivative, which is cosine hyperbolic, right? That's all the information you need about these two. And then the expression becomes, so I'll write the whole thing out first, and then I'll replace this with the integration by parts formula. So write the entire expression out. You don't have to write as much. I'm just trying to be very thorough, very clear. So parentheses, and that's where the integration by parts goes in. So that will be uv, e to the 2x, minus the integral of v du, so 2 e to the 2x cosine hyperbolic x dx. Now we're exactly back at where we started. So finish writing this out. And like I said, you don't have to write as much. It's important to write a little bit. I'm just trying to be clear. And then the problem is that we want to find out what this is. And I have another integral that's exactly the same to solve. But the positive is that now the two integrals have different coefficient. This is 1 of it, and this is 4 of it. So they won't cancel out. If it turned out that this is 1 and this was 1 as well, these would cancel out, and that wouldn't help me at all. But they don't cancel out. So that means I could rename this thing, which is the thing I want to find out. Could rename this something. Maybe I'll call it I for integral or something. So big capital I. So then my expression turns into I equal to e to the 2x sine hyperbolic x minus 2 e to the 2x cosine hyperbolic x plus 4i. And now you can see how easy it is to finish this up. Once we've got here, right? I have 4 i's and 1 I. I want to find out what I is, so I can just move over the entire thing to the other side, right, and get that 2e to the 2x cosine hyperbolic x minus e to the 2x sine hyperbolic x equals 3i, and then divide by 3 to get that I equal to 2/3 e to the 2x cosine hyperbolic x minus 1/3 e to the 2x sine hyperbolic x. And then remember that I was e to the 2x cosine hyperbolic x dx, and that means this equals to 2/3 e to the 2x cosine hyperbolic x minus 1/3 e to the 2x sine hyperbolic x. This is the answer. So this is another common trick when you're dealing with integration by parts. You use integration by parts twice so that the original integral shows up again, and you move it over to the side, to the left side, so that you can handle it as if it were a variable, right? As if it were an unknown, which it is. You can't also forget, and I have forgotten that, to add the plus c at the end. Whenever you don't have two integrals equal each other, this is actually the correct step in which you have to add the constants. While you have one integral on one side and the another integral on the other side, you don't need the plus c. You may write them if you want, but you strictly need them once you have the integral on only one of the sides. So you need the plus c. So don't forget the plus c, and try and understand what happened here. This is pretty cool, and will happen very frequently, especially when you have two expressions, one of which doesn't matter how many times you derive, it never goes away, and the other doesn't matter how many times you integrate or derive, doesn't go away. That's prone territory for this type of strategy. So I could use, instead of cosine hyperbolic, I could use cosine or sine. Instead of exponential, I could also use cosine times cosine hyperbolic. I could do a bunch of different combinations, but they would all lead more or less the same way. So make sure you understand the process as well.